Okay, good morning. In today's session also, we'll be discussing about some examples on overhanging beams to draw shear force and bending moment diagrams for overhanging beams for different load conditions. We'll take one or two examples and we'll discuss. As a first example, let us consider this overhanging beam subjected to UDL, a point load, and a horizontal load also at point C, producing a couple here at C. So here the equivalent beam for this, the equivalent beam for this can be written, can be taken like this. And for this point load, horizontal point load, we can replace it by a couple 5 kilonewton meter, because the distance at which it is acting is 1 meter. 5 into 1, 5 kilonewton meter, clockwise couple. And a horizontal load actually we can consider. We can replace this force 5 kilonewton by a 5 kilonewton horizontal load and a couple 5 kilonewton meter acting at C. So this 5 kilonewton horizontal load, as far as the shear force and bending moment diagrams are concerned, it will not have any effect. So we don't consider this while working with shear force and bending moment diagrams. Okay, so we consider now only the couple acting at C. Okay, now to find shear force and bending moment at various sections, we consider different sections in various segments. Okay, here we have to consider three different sections, one between A and C, the second one between B and C, and third one between B and D. Okay, action. And origin we can take from A or B, it doesn't matter, whichever is convenient we can take. For a section between AC, we will take origin at A. For the remaining two sections, we will take origin at D. Origin at D. Okay. Now with this, we will proceed to first section between AC. First section between AC. So for this section between AC, considering left hand side, that is origin taken at A. Okay. One second. Before that, we will find the reactions actually. So to find reactions RA and RB, we apply the conditions sigma MA equal to 0 and sigma Fy equal to 0. Two conditions we will apply to find the reactions RA and RB. Okay, RA and RB. So by applying the condition sigma MA 0, we will have RB into 6, RB into 6 is equal to in place of this, we have a couple acting 5 kilonewton meter. We can replace this by couple. Okay. Now the moments due to UDL 2 into 4 into 2. 2 is distance of resultant plus 5. This is a couple already, so we don't again multiply with the distance. Plus 10 into 8. Okay, 10 into 8. So now we will get reaction RB as 16.83 kilonewtons. Okay. Once you get RB, we can find RA by applying the second condition, sigma Fy 0. That is RA plus RB is equal to total downward load, which is 2 into 4 UDL plus 10 point load. That is 18. Therefore, RA is equal to 18 minus RB 16.83. That is 1.17 kilonewtons. Okay. So next, once you find reactions, then we'll find shear force and bending moment at different sections. First, let us consider section in AC portion with origin at A. What is the shear force now at section? Shear force at section X is RA, that is 1.17 minus UDL 2x, total UDL to the left of the section. Okay, total UDL to the left of section. So now the limits for X are 0 to 4. In portion AC, X varies from 0 to 4. So at X0, the section will be at A and shear force at A is 1.17 minus 0. That is 1.17 kilonewton. It is positive only because the convention that we follow is left side upwards is positive and right side downwards is also positive. Okay, and vice versa. Similarly, at X equal to 4, the section will be at C and shear force at C is 1.17 minus 2 into 4. That is minus 6.83. So if you observe, the shear force is changing sign between A and C, which means it becomes 0 at one point. Shear force becomes 0, changing sign at one point from positive to negative. Okay. So to find the location of that point where the shear force is 0, we equate SF shear force at X to 0. This to 0. This implies 2x. 2x is equal to 1.17 or x is equal to 0.585 meters. So at x equal to 0.585 meters, the shear force changes sign, at which the bending moment is maximum. At x equal to 0.585, bending moment will be maximum. At the point where the shear force changes sign, bending moment is maximum. Okay, that is the condition. Now let us see bending moment. at x. Considering again left hand side of section, considering left hand side of the section, bending moment is RA into x 1.17 into x minus total UDL is 2x into x by 2. So 1.17x minus x square. So this is the bending moment. Now at x equal to 0, bending moment at A you will get. That is 0. And at x equal to 4, you will get bending moment at C at 4. That is 1.17 into 4 minus 4 square, which comes out to be, bending moment at C comes out to be minus 11.34 kilonewton meters. If you observe here, bending moment is negative at C and 0 at A. In between, its variation is parabolic. That is clear from this equation. Okay, it is parabolic variation, and at some point, that is at x equal to 0.585, it will have maximum value, which may be positive. Generally, here it is positive, maximum positive value at x equal to 0.585. Okay, so at x equal to 0.585, bending moment is equal to maximum, actually positive bending moment, 1.17 into 0.585 minus 0.585 square x square. So which comes out to be 0.342 kilonewton meters. We will be getting this positive plus 0.342 kilonewton meters. Okay, that's clear. So between A and C, the bending moment also changes sign. Bending moment also changes sign. Okay. It means from A you will have, so between A and C, bending moment also changes sign, because the maximum bending moment is positive and bending moment at C is negative. That is minus 11.34. It means bending moment is changing sign at some point between A and C, which is the point of counterflexion. Okay. Next, consider the section between B and D. Here, so you have only one force acting in this portion. This is the overhanging portion. Okay, and the limits for x are from 0 to 2. The limits of x are from 0 to 2. So shear force at x is 10 kilonewtons. Okay, right side downwards it is positive, and which remains constant from B to D, because it is independent of distance. Okay, so shear force remains constant at 10 kilonewtons between B and D. Okay, now coming to bending moment, it is negative because it is hogging moment, so it is taken with a negative sign. Okay, bending moment is minus 10x. So bending moment at D, that is at x equal to 0, is 0, and bending moment at B at x equal to 2, it is minus 20 kilonewton meters. Okay, now consider section between B and C with again origin at D only, origin at D. So consider the section between BC. The limits for x are 2 to 4 because we are taking origin at D. The limits are 2 to 4. So now what is the shear force at x? Shear force at the section. Plus 10 minus RB. RB is 16.83. So it is minus 6.83. And this remains constant between B and C because there is no load acting. Okay. So shear force at B equal to shear force at C equal to minus 6.83 kilonewtons. Okay. Shear force at B here is, it is to the left hand, just to the left. Coming to this shear force at B here, it is 10. It is just to the right. Just to the right of section B, it is 10. Just to the left, it is minus 6.83. That means at B, there will be a sudden change in shear force because of the reaction RB. Okay, that change is equal to RB. Now bending moment at X is 16.83 into X minus 2 RB into X minus 2 minus 10X. Okay. Now here bending moment at B. Bending moment at B, that is at x equal to 2. This term becomes 0 and minus 10 into 2, that is 20 minus. Same as this. Okay. This is at x equal to 2. And at x equal to 4, bending moment at C is, substituting 4 here, 16.83 into 2, that is 4 minus 2, minus 10 into 4, minus 10 into 4. So you will be getting the bending moment as minus 6.34 kilonewton meter. So bending moment at C is negative minus 6.34. If you observe this bending moment at C here, it is 6.34 minus 6.34. And when you consider AC, we got bending moment at C as 11.34. This is just to the left of section C, and just to the right of section C it is minus 6.34. There is a sudden change in the bending moment, if you observe here, by 5 units, 5 kilonewton meter. That is because of couple acting at C. Okay, where there is a couple acting, there will be a sudden change, sudden decrease or increase in the value of bending moment. Okay, so the sudden change of 5 kilonewton meters occurs at C. So this is how we'll find out the bending moments and shear forces. Next, we can calculate we can locate actually the contraflexion point of contraflexion, okay, which occurs between A and C, that we have seen here. Okay, so by equating this to 0, you will get x into 1.17 minus x equal to 0, or x equal to 1.17 meters. So x cannot be 0 here. So at x equal to 1.17, you will have the bending moment changing sign, becoming 0. Understand? This is the location of point of contraflexion. Now we can draw the bending moment and shear force diagrams. We have calculated all the values. considered three sections. Okay, so shear force at A is 1.17, shear force at C is minus 6.83. It is uniformly changing. Shear force variation is linear, which is clear from this equation. Okay, so now to draw the shear force diagram, at A it is 1.17 and at C 6.83 minus. So it varies from plus 1.17 to 6.83. Okay, and changing sign here at this point. Let us call this as point E. Okay, which is at a distance of, at what distance is it? 0.585 meters. Okay, from here. This is 0.585 meters. Now, between C and D, B, C and B, the bending shear force remains constant. Okay, at 6.8. At B, you will have sudden increase in the shear force because of reaction. And between B and D, the shear force again remains constant at 10. So this is positive shear force and negative shear force we will have here. Coming to bending moment diagram, bending moment at A is 0 and bending moment at D is also 0, and at B it is minus 20. Okay, linear variation. Understand? And from what is the bending moment at C here? Bending moment at C is, bending moment at C is 6.34 just to the right and 11.34 just to the left. Okay, 11.34 just to the left, minus 6.34 and minus 11.34. This clear? Yeah. And bending moment at A is 0. Bending moment at A is 0. And it becomes 0. Bending moment becomes 0 at a distance of 1.17 meters. Bending moment changes to, bending moment changes sign, that is the point of contraflexion, is 1.17 at a distance of 1.17 meters from A. So here you will have maximum. Maximum means 0.342 only. It is okay, positive. It is generally when not drawn to the scale, actually very small, 0.342 means. Okay, and yeah, it varies linearly. From A to C, it is parabolic only. Okay, from A to C, it is parabolic, and it varies up to 11 point, sorry, it varies up to 11.34, and there will be a sudden change here to 6.34 by 5 units, okay, because of the couple. And from 6.34 it changes to 20, okay, from 6.34 it changes to 20. This is linear variation, straight line. So positive bending moment is here. This distance is 1.17, point of contraflexion this is, and this is the point of maximum positive bending moment, okay. This is how the bending moment diagram will be. Actually it is to be shown like this. Yeah. Okay. This is okay. So this is the bending moment diagram and shear force diagram for the given. Let us take another example, which is two sides overhanging beam, overhanging on either side, both sides. Okay. Suppose supporting UDL and point load. Let us consider now the second example of overhanging beam on either side, overhanging at both the supports A and B, and supporting a UDL and point load here. So now, as usual, we find the reactions RA and RB. So applying condition sigma MA0, you will have RB into 11, okay, that is anti-clockwise actually, okay, RB into 11, and the portion of UDL to the left of A also produces anti-clockwise moment. So the moment of this UDL 30 into 3 into 1.5, that is also anti-clockwise. That is equal to moment of the UDL lying to the right of A, which is for a length of 5.5 meters. Total length is 8.5 of UDL. So 30 into 5.5 into half of that is 2.75. Okay, plus 100 into 11 plus 4, 50. Okay, so this gives the reaction RB as 165.3 kilonewton. Now we can find RA as total downward load 30 into 8.5 plus 100 minus RB 165.3. So which comes out to be 189.7 kilonewtons. Okay, 189.7 kilonewtons. So first we have to find the reactions before proceeding to calculate the shear force and bending moment. Once you know the reactions RE and RB, then it becomes easy. Now, how many sections you have to consider? You just observe. We need to consider 4 sections. Okay, 4 different sections we have to consider for finding out the shear force and bending moment at various sections. Okay, the first section we consider is between AC, taking origin for this at X, at C. Sorry. Similarly, for second section also we'll take origin at C. For third and fourth, we'll take origin at E. Origin at okay. So consider first the section between AC. The limits 0 to 3. The limits for X are 0 to 3. Now consider the shear force and bending moment here at section X. So left side downwards you have the UDL acting downwards and left side of the section. So it is negative minus 30x minus 30x. Okay. So the variation of shear force is linear. Okay. From this equation it is clear. It is straight line equation. Okay. Now substituting x0 and x3, you will get the shear forces at x0 means shear force at C 0. At x equal to 3, shear force at A is minus 30 into 3, 90 at A. Okay. Next, bending moment at section X. Minus 30 into x by 2. Okay. Only UDL is acting to the left. So it is negative because it is hogging moment. Okay. So 15x square is the bending moment at section X. Okay. Now at x0, bending moment at C is 0. Okay. Now at x equal to 3, we will get bending moment at A as 15 into 3 square, that is 130. 135. Sorry. Shear force at A is 0 and shear force at shear force at C is 0. At x is equal to 0. Shear force at C is 0 and x equal to 3. Shear force at A is minus 90. Coming to bending moment, it is minus 15x square. Okay, bending moment is minus 15x square. So bending moment at A, that is at x equal to 0, is 0. And bending moment at, it is bending moment at C is 0. And bending moment at A, that is at x equal to 3, we will have minus 135 kilonewton meters. Okay. Now take the section between AD. Section between AD with origin at C. With origin at C. So the limits for x are 3 to 8.5. 3 to 8.5. Okay. Now the equation for shear force at section X is 30x minus 30x plus RA. What is RA? 189.7. 189.7. Okay. So here at x equal to 3, we'll have shear force at A minus 90 plus 189.7, that is 99.7. And at x equal to 8.5, shear force at B is minus 30 into 8.5 plus 189.7. Okay, 30 into, so it comes out to be 65.3, actually, minus 65.3. Okay, so if you observe, the shear force varies from positive to negative. At some point, you will have maximum shear force changing sign where the bending moment is maximum. Okay, so you will get that point by equating shear force to 0. You will have x equal to, by equating shear force to 0, this equation, you will get x equal to 189.7 by 30. So 6.32 meters. 6.32 meters. Okay. So at this point, you will have maximum bending moment. Now you find the bending moment equation. So it is 189.7x RAX minus 15x square. RAX into 15x square. So this gives bending moment at various points between A and D. Okay. The limits are being 3 to 8.5. So at x equal to 3, bending moment at A is this is x minus 3, 189.7 RA into x minus 3. This distance you have to take. Okay, RA into x minus 3 here. So at x equal to 3, it is 0 minus 135. So it is 135 minus 135 kilonewton meters. At x equal to 8.5, we will get bending moment at D 189.7 into 8.5, 8.5 minus 3 minus 15 into 8.5 square. Okay, 15 into 8.5 square. So you'll get bending moment at D as minus 40.4 kilonewton meters. Okay, understand? So in between, we will have maximum positive bending moment at a distance of 6.32. So at x equal to 6.32, at x equal to 6.32, bending moment, that is maximum positive bending moment, is 189.7. 180 bending moment is equal to 189.7 into 6.32 minus 3 minus 15 into 6.32 square. So which comes out to be 30.7 kilonewton meters. Okay, 30.7 kilonewton meters, which is maximum positive, which occurs at a distance of 6.32 meters from C, left support. Okay. Here. Now consider the section between B and E. Consider the section between B and E with origin at E. With origin at E. So the limits are 0 to 4. X varies from 0 to 4. So shear force at X is plus 100. As per the sign convention, it is positive. So shear force at B and shear force at E are equal 100 kilonewtons. And bending moment at X. Bending moment at X is equal to minus 100x, because it is Hagen bending moment, it is negative, minus 100x. So at x equal to 0, okay, bending moment at E is 0. At x equal to 4, bending moment at B will be minus 400 kilonewton meters. Okay. Now consider the section between B and D. Consider section between B and D. The limits for x are, origin is taken again at E only. X varies from 4 to 4 plus 5.5, 9.5. 4 to 9.5 are the limits for x. So shear force at x is equal to 100 minus RB. What is RB? 165.3. So it is minus 65.3. It remains constant. Okay. So shear force at B and shear force at D remains constant at 65.3 kilonewtons, because there is no other load acting. And coming to bending moment. So 165.3 RB into X minus RB into X minus 4 minus 100 into X. Okay. So substituting X0, X varies from 4. Substituting X4, we will have bending moment at B. This term becomes 0 and bending moment at B is 100 into 4. Next, at X equal to 9.5, we will have bending moment at D, which is 165.3 into 5.5 minus 100 into 9.5. So this comes out to be minus 40 minus 40.4. Okay, minus 40.4. This clear? So bending moment at D is minus 40.4. Now, knowing all the values, we can plot the bending moment diagram for this now. Okay. And before that, what you can do is, you can locate the point of contraflexure actually. Okay, that we'll see later. First, let us see the shear force diagram for this. At C, the shear force is 0. At A, the shear force is minus 90. Okay. Next, coming to E, shear force is 0. Coming to E, the shear force is 0. And at B, it is positive. Shear force at B is positive actually, 100. Okay, which remains constant. Next, 65.3. Shear force at B is 65.3, which remains constant up to D. Which remains constant up to D. Okay. It remains constant at 65.3. Next, between A and D, the variation of shear force is linear actually. The variation of shear force is linear. So the shear force at it is 90 here. It is 90. Okay. And at here it varies to positive 99.7. Okay, because of reaction, there will be a change in the value, and it varies to 65.3 here. And this distance is found to be 6.32, where the shear force is changing sign. Okay, where the shear force is changing sign. At this point, you will have maximum positive bending moment. Okay, which is found to be, yeah, this point is H అనుకుంటే bending moment at this point H is 30.7. It is calculated as 30 points. Now coming to bending moment diagram, we will have negative bending moment here from C to A. So bending moment at A is 135. Okay. Bending moment at A is 135. Minus 135. Similarly, bending moment at B is minus 400. Minus 400. And bending moment at D minus 65.3 minus 65.3, sorry, minus 40.4, minus 40.4. Bending moment at D is minus 40.4 and at 6.32 it is 30.7. Bending moment is 30.7 positive at this point H. So it varies parabolically between A and D. Between A and D, it varies parabolically. Is this clear? Now, this variation is linear. It varies to 400. Okay, this is straight line. This is parabolic. Okay, in the portion of UDL, the variation of bending moment is parabolic. Okay, and where there is no load, it varies linearly. Bending moment varies linearly. So, this is the bending moment diagram for the given beam, and this is shear force diagram for the given beam. Okay, and these points where the bending moment is changing sign are called points of contraflexure, which can be located by equating bending moment equation to 0. By equating bending moment equation between A and D, between A and D, the equation for bending moment is this one. So equating this to 0, you will get the values of x. Okay, that is how we draw the shear force and bending moment diagrams, finding the salient points in the beam. Okay, that's all for today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.